Hello, and welcome to the Earth SciShow podcast, the podcast that explores the latest discoveries of Earth and beyond. And I'm your host, Mr. Earth Guy, and today we'll be talking about a groundbreaking study that reveals the secrets of Mars's core. Mars is a fascinating planet that has captivated scientists and explorers for centuries. It has a rocky surface, polar caps, volcanoes, canyons, and ancient riverbeds. But what lies beneath its crust? What is the structure and composition of its core, and what does that tell us about its origin and evolution? To answer these questions, we need to look at seismic waves. These are vibrations that travel through the interior of a planet when it's shaken by events like earthquakes or impacts. By measuring how these waves propagate and reflect, we can infer information about the layers and properties of the planet's interior. That's exactly what the InSight mission has been doing since it landed on Mars in 2018. It's a NASA-led mission that deployed a broadband seismometer on the surface of Mars to detect and record seismic activity. InSight has detected dozens of Mars quakes and other seismic signals, revealing the layered nature of the red planet. It has also recorded reflections from a large impedance contrast that is interpreted as the core mantle boundary, or the CMB. This is the boundary between the rocky mantle and the liquid iron alloy core at the center of Mars. But until recently, no seismic waves had been discovered traveling through the core of Mars. These waves are crucial for understanding the constraints of the elastic properties and composition of the core, which are poorly known compared to other planetary bodies. That's why a new study published in April 2023 in the Journal of PNAS is so exciting. It reports the first observations of seismic waves propagating through the Martian core. These observations were made using data from two far-side seismic events detected by InSight. The authors of the study identified a core transiting seismic phase called the SKS from these two events. SKS travels as a shear wave in the crust and mantle and as a compressional wave in the core. By measuring the travel times of the SKS relative to the other mantle transversing body waves, they were able to constrain properties of the core and construct models of its elastic behavior. Their results show that Mars has a smaller and denser core than previous estimates, with a radius of about 1,800 kilometers and a density of about 6.2 grams per cubic centimeter. They also show that Mars's core has a low p-wave velocity of about 4.9 kilometers per second at the CMB, indicating that it contains a high fraction of light elements such as sulfur, oxygen, carbon, and hydrogen. These findings have important implications for understanding how Mars formed and evolved over time. For example, they suggest that Mars's core may have cooled faster than previously thought, leading to the cessation of its global magnetic field early in its history. They also imply that Mars's core may have had a distinct molten layer at the top, which could affect its thermal and chemical evolution. The study also demonstrates the power of seismology as a tool to probe planetary interiors. By using seismic data from a single broadband seismometer and relatively small seismic sources, the authors were able to make unprecedented observations of Mars's core. They hope that future detections of core transiting waves will help refine their models and reveal more details about Mars's central interior. That's all for today's episodes on Earth SciShow. I hope you enjoyed learning about this amazing discovery and what it means for our understanding of Mars and other rocky planets. If you want to read more about this study, you can find a link to the article in our show's notes. And if you like our podcast, please don't forget to subscribe, rate and review us on your favorite platform. Thank you for listening and stay tuned for more episodes on Earth SciShow.